Thank you for the introduction. My intention here is not to give a talk for specialists in random geometry. I see one or two in the audience. It's not for you. This is the intention is to actually go through some stuff that is, as I've tried to learn some of the things of Scott and others, and I sort of have a perspective, and I want to use this opportunity to try to maybe give people an introduction so they can understand it a little bit. And I think I want to press the idea, I'm as a senior mathematician, that going over things and finding new perspectives and things like that is a very useful thing to do. So there are various things. There's the fractal curves where I got involved in the Schramm-Loewner Evolution, its variants. But more recently, let's say now at this point now 20 years, there's been a lot of study in random geometry which can take it from different perspectives, from discrete perspectives, from continuous perspectives. For the continuous perspectives, the main characters are the Gaussian Free Field and various forms of its exponential. There are various ways of looking at these things, and I'm not saying one's better than the other, but for my own sake, I prefer the idea of exploration, and I want to take this as a way to introduce people who have not seen this. I will assume people have a little bit of knowledge of probability through basic Brownian motion and stochastic calculus, but not that they've seen the random geometry. Let's see. Oh, it's just this is slow. It's funny. Okay. There we go. I'm not going to give a list of results. I'm going to put a few names up: Schramm, Sheffield, Miller, and ... and just tell you there's a lot of people in the ... that are being left out. But I'm not planning on discussing all the great things that have been done by people other than me. And I'm just going to, I'm going to mention there are notes of Nathaniel Bereznicki, which my reading of this with students and postdocs in Chicago led to a lot of my thoughts. So some of the things I say will not be found in his notes. It's more my trying to understand his notes. Okay, just very philosophical. So you can flip a coin an infinite number of times. This is the basics of probability. And in fact, this is all of probability. Any system that we have, we don't know how to handle more randomness than that given by a countable collection of coin flips. We just have various different ways of packaging it. Probably the one I'll be using the most today is where I split that infinite set into a countably infinite sets, give me a countable collection of coin flips. I can give you one normal random variable. They'll have independent normal random variables. When you do this thing mathematically, one often likes to think of having a space where everything lives. Or sometimes you have the idea dynamically of exploring, and when you explore, you don't flip the coin till you need it. And somehow the exploration viewpoint is the kind that I'm going to be taking today. So I'm going to start with what we'd learn in basic probability, maybe basic statistics, the idea of a multivariate Gaussian distribution. Centered means mean zero. So here's some basic facts. We start with our input. Someone gives us a bunch of independent normals. Here I gave a finite, but it could be a countably infinite set. And then the Gaussian distribution is some collection Zj. And the thing about the Gaussian distribution is you can always write the value at Zj as the expected value of what you've seen up to that time, plus an independent Gaussian random variable. And in fact, this expected value is actually linear in the values that you've seen. Now, this constructs the Gaussian distribution, but the interesting thing from our perspective is that the order in which I gave the points doesn't make any difference. So I can actually, if I have this thing, I'll look at one, I'll look at another, now I'll say, which one do I want to look at now? I'll look at this one, I'll look at this one. And the distribution of the final object doesn't depend on this. So a particular case of this is what's called a discrete Gaussian field in Z2 here. Let's take a strict subset of Z2. I want that so the random walk Green's function is finite. So I take this subset, I give it an ordering, any ordering that I wish. I'm just going to let AJ be that set with the first J minus 1 removed. And then if I want the discrete Gaussian field in Z2, I start with my randomness. I come with my Gaussian random variables. And then I'll let phi j xk mean the expected value at xk, given I've seen the first j random variables. Well, it's what I've seen from the first j minus 1 plus 3 terms. One is my independent Gaussian. Then it's multiplied by a certain factor, which is how much new randomness there is at this time. And then there's this thing here, which is the Poisson kernel, which tells me how much this affected me at xk. And you just add that up. And it's an exercise to check that, in fact, this is a joint normal distribution with the Green's function given by the random walk. And it constructs it. And again, the Green's function doesn't depend on the ordering, so this doesn't depend on the ordering. Covariance function, covariance. What did I, oh, covariance function. The covariance function of the normal is the Green's function of the, yeah. Sorry about that, yeah. And just so basically, think about, oops, sorry. Okay, the ordering gives the square root. If I'm only interested in the final thing, then I can choose any ordering that I want. Absolutely, yes.
So is this particular way that you show here important beyond the order? Or it's just another way of saying that you have Gaussian vector with covariance?
But the lesson is that this is one way to construct this thing, and this is going to be the useful way to think about it today. That's the lesson. And in this construction, there are two pieces of randomness. So there's the random walk, which gives the covariance function. The Green's function of the random walk gives the covariance function. And then there's the independent normals that are actually giving the realization. And I'll say this definition extends to symmetric Markov chains and more generally Hermitian symmetric complex weights on edges. Very generally. In fact, a lot of the traditional way of doing this just uses matrices and different, and as pointed out there, different square roots of the, yeah. Okay, it takes a while from, it's kind of funny, yeah, it takes a while for, this comes immediately, it takes a while to get to there. So I want to take the same viewpoint for the continuous. So there are various ways of doing the Gaussian free field in the upper half plane, and I want to take this sort of view to it. I'm going to do some drawing here. I'm going to do a field with a certain Green's function, and then I'm going to explore the field up here. What's an exploration? An exploration will be an ordering of points. It will be a curve. This curve is basically the order of points. I will do my exploration along there. Maybe there's some point here that I'm doing this. My independent Gaussians now become a one-dimensional Brownian motion. That's just a one-dimensional Brownian motion. And this expression we had before for the discrete case becomes this in the continuous case. So there's Z. This discrete collection of normals becomes DWT. This, how much new randomness is added becomes, I'm just giving it a name, I'll get rid of this very soon. And then we have this Poisson kernel, which in this case corresponds to what's the probability a Brownian motion starting here leads the slit domain at here. Let's not worry about the exact definition. And let's just make this a little more precise. So we take here, so first thing we'll do to make this a little more precise is to use conformal invariance. Brownian motion is conformally invariant. So I will map the slit domain and this goes, so it's called the Liouville equation. So I'll take a map of the slit domain to the upper half plate. I will choose a particular choice from the which has this expansion at infinity. Now this A, I've just chosen some parameter A, which is going to be 2 over kappa. And we're going to say at infinity, it has this expansion. That makes it unique, assuming I parameterize the curve correctly. So I've reparameterized this curve in a way so that the average amount of randomness being added to the system stays constant. That's what the A does. So there exists a real value function. So this is just a Liouville equation, describes this function. And it says that its time derivative is given by this. And now I will often write ZT, so this sends this point to a point here, UT. I'm often going to normalize, so I send it to 0 instead. And then this is just a definition. I'm going to write 1 over ZT as real part minus I imaginary part. Well, that's just a definition of HT. And for those who know the Poisson kernel, that's basically the Poisson kernel in the upper half plane. So I'm just using it like that. And then we could just write phi of Z as, that's an almost precise expression. It's almost precise, but it is a problem because the stochastic integral blows up as the curve approaches Z. So now, just to be a precise definition through our math conference, suppose I have a compactly supported measure on H. Such that, let's see, I think I have the previous slide. No, I have 2 slides ago, sorry. That's just the Green's function of the Laplacian in the upper half plane. I've chosen the constant 1 there. Oops, wrong way. So if I take a compactly supported measure so that the Green's function is finite. And now I just average this rather than looking at Z, I look at it phi of rho, and just simply the same basic expression, except that instead of doing HT of Z, I do the average with respect to rho and write the same expression. Then it's just an exercise to show that phi of rho is a centered Gaussian random variable with variance. Here, cap over 4, that's the A, that's the A's involved, cap over 4 times GH. And I'm not going to go through this, but it's straightforward computation using stochastic calculus. I say with Hadamard's formula, but really you prove Hadamard's formula with the stochastic calculus, what you need. You just need the stochastic calculus. If I've chosen, now this is a little tricky if you've never seen it, you can choose curves in the upper half plane that are plane filling. So if I choose a curve that will eventually visit everything there, then this actually is a definition of the Gaussian free field in the upper half plane. And it comes with it, basically the definition is conformally invariant. The Brownian motion, the Green's function is conformally invariant, so this is as well. I also say you can also do the same thing with non-simply connected domains. You can't do exactly this way of normalizing things, but you just have to normalize somehow what the Poisson kernel looks like there. Now, in practice, one often explores for the curve that's not space filling, it only explores part of the thing. So if you suppose I explored maybe with an infinite curve, but that was not space filling, and then I looked at Z, well then the conditional expectation given the field on the curve is well defined. It's well defined if Z is off that curve. And then if I want the entire GFF, I have to explore this, and then I have to look at the rest of it. I often call the rest of it the residual field term from statistics. What's the randomness that's still left after saying this part? I'll say for me, reading physics literature where the people take expectation values of fields or derivatives of fields or things like this can be understood. If I want expectation values at a few different points, it's very useful to do this. Take a curve that separates those points and don't worry about the rest of the field, only the separating part, and then you get things into actual expectations. But that's not my main thing I want to talk about today. Wrong way. Okay. All right. In the Liouville equation, we could choose any real valued function ut, and that would give me a different curve. I can choose any curve I want. I might actually choose a curve that's independent of wt. But even more than that, this is important. When I'm exploring the curve, there's no reason why I can't look at what I've seen already to make my decisions as to where to move next. So I can allow the curve, my random curve, to depend on what I've seen, but not the future. And for probabilists, that's basically saying that the ut has to be adapted to the Brownian motion, wt. You're allowed to see the wt. And then the coupling of SLE and GFF occurs when you actually use the same Brownian motion for this ut. Let this Brownian motion be exactly the Brownian motion you have that's constructing your field. So this leads to the Schramm-Loewner Evolution, which is not the topic of today's talk. And this is actually predates the other discussion in terms of, but this goes back to Oded Schramm at the turn of the century, where he was looking for possible limits of curves. And he showed that under certain assumptions called domain Markov property and conformal invariance, the only possible curves are those given by the Loewner equation. I've written it slightly differently than the way he did, but they easily seem to be equivalent, where I took a standard Brownian motion here, and then I put some parameter here. The parameter is only called kappa, and in this writing, A is equal to 2 over kappa. But this is called SLE kappa. So I will not give a lecture on this, but I'll just tell you a few things about this. For kappa less than or equal to 4, this produces a simple curve, a simple fractal curve, the exploration curve. For kappa between 4 and 8, it has double points, but is not plane filling. So that's kappa less than or equal to 4. Kappa between 4 and 8, something like that. And then for kappa bigger than or equal to 8, it's plane filling, and I'm not going to try to draw a plane filling curve. And the Hausdorff dimension of the paths is actually given by 1 plus kappa over 8. But I want to talk a little bit about this, and this goes back to some of the early results of Schramm and Sheffield. When we do this coupling, so if I do this coupling, so we have the UT of Brownian motion, then I can actually look at where this point is going. So that's ZT. I subtracted UT with WT. And let me just let theta T of Z be the argument of this. And basically, Ito's formula, so you can do Ito's formula on this, and you get this. So argz is just the initial condition at time 0. And let's just look at the case where, actually let's look at the case cap equals 4 for here, because it's the easiest case. Cap equals 4 is the nicest case where this term actually even drops out.
What is the prime on?
That's the Z derivative. The primes are Z derivatives. Sorry. So I use dots for time derivatives, primes for Z derivatives. And you get this. So what happens here, let me just draw a picture. And I try to draw the upper half because that's easier to see in the back of the room. This is kappa. So here's kappa equals 4. That's just argument of 0. Well, you actually put argument pi there, and you basically get, you construct a field, the Gaussian field, by taking an SLE curve. After you've taken the SLE curve, you extend, you put Gaussian fields on both sides here, except on this side, you add a pi, because that's theta infinity of Z on this side, theta infinity of 0. So we constructed this thing, so we've constructed the field, but after we constructed the field, we had this curve going through it, which is a jump in the Gaussian field. I should say for the way that I'm doing it today, when I take a particular kappa, then I'm doing the Gaussian field with covariance kappa over 4. There's a relationship. The kappa equals 4 is constant 1. So this very simple idea actually constructs the field with the curve inside of it. Suppose you're here and you map it back. If you're on this side of the curve, the image of this has angle almost pi. If you're on this side of the curve, it has angle almost 0. And the limit has angle 0, angle pi. That's all that's happening. And this happens for other values of kappa less than 8, except that you do get an extra term, which is this is well defined. This is this argument, but it's another term to this. And you can do this with multiple SLE paths to give fields with several jumps.
What is the point of this construction? I feel like this is a punchline. So now we've constructed this random curve and this random field, and now what?
Okay. So I was asked a good question, why do this? And that's too big a question for this talk. There's an interplay back and forth between understanding what the field looks like and understanding what these curves look like, which go back and forth, and that's a lot of the ... So this is sort of an introductory to.
You're saying that this coupling provides
Yes.
to study independent.
I mean, this is a, so, oh no, I'll do it. What we've done is created what might be called a level curve of the Gaussian field. That doesn't quite make sense because it isn't exactly equal to pi here, it isn't exactly equal to 0 here. But this, so we have constructed a level curve of this field. And in the case cap equals 4, the GFF, which is the easiest case, the level lines of the GFF actually are SLE curves with cap equals 4. Now, I do want to say something, a technical issue on this. What I'm doing here is kind of cheating, or it doesn't quite do mathematically everything. So there are two things to do. One is to start with a field and find the SLE curve. What I did is cheated in some sense and started with the SLE curve and created the field. And if you actually look in the proofs of Schramm and Sheffield, they do that in the proofs. But there are questions of, if you gave me the field using a different definition, lots of definitions of the Gaussian field, how easy is it to find the curve in there? And I'm not dealing with that question today. I'm more here just trying to understand. This is an introductory talk. Yes. I'm going to go back one. So that's the upper half plane. I also want to talk about the full plane GFF, or if you wish, this GFF on the sphere. The same idea works. If you have the sphere, you can take a space-filling curve of the sphere. But for them, the natural parameterization is not 0 to infinity, but minus infinity to infinity. And you end up getting the value at z at time t, given what you've seen, is equal to this. Well, it turns out this blows up at minus infinity as well. So this is not well defined. But if I take two different points and take the difference, this is well defined, assuming the curve hasn't hit z or w yet. There's also going to be blowups when it hits z and w. So basically, the same idea. We take a signed measure, but we have the integral of rho of the measure be 0, so that we have this cancellation. And then it's defined. And then part of this construction shows you, given an initial segment, the remainder of the field is given by adding a Dirichlet GFF calculus. So once you get started, we go back to the original problem. Getting started, you have to deal with that infinity. Wait a second here. Okay, now what I want to do is talk about a variant of the construction of GFF cap on the sphere, which is a little closer to what you'll see in the physics literature, maybe a little, but, what we're going to do is do a two-step process to construct a Gaussian field. We're going to construct a random curve. Then we're going to look at the field, independent field, on the random curve. And then we'll add the rest later. So here I need a little bit of drawing. So actually, the best thing is actually have a loop. So we're going to choose a random loop. Now, I'll just say, choosing a random loop on the sphere is a little tricky. The natural measures on random loops tend to be sigma finite infinite measures, not finite measures, but I'm not going to worry about that detail. This is going to look like an SLE kappa. And now, for most of what I do now, I'm going to restrict myself to kappa less than 4. So I've got this kind of loop. And what I'm doing is, maybe I'll see some of the loop. Maybe I'll actually draw this. Maybe this is where I started. and maybe I've seen this amount of the loop, and this yellow I haven't seen in the future. So I will see the loop, I will see the field on this loop, and then I'll add things there. Now, what I want to do is use conformal invariance. So now we imagine we have seen an initial start of the loop, and we have seen the field on that initial segment. So one of the statements about the curve, what makes this an SLE loop, is that the distribution of the remainder, given this, if you can talk about that, is the SLE I talked about before, just by conformal invariance. So the natural thing to do is take this initial segment and map it to the upper half space. That's going to infinity.
So this is an SLE bridge you're positioning where it ends up.
That's part of the tricky parts. We want something that's invariant under Möbius transformation, so we don't really want to quite exactly specify how big it is, where it is, or anything else like that. So eventually what I'm going to talk about won't need to make that specification, but this is a good thing to have in one's mind. Okay, so we have that. I'm just going to draw this. We haven't seen that yet, but that's going to come at some point. And note, we do have two sides to this. I'm not sure I got the orientation right, but you have two sides of that. So first thing, let's talk about this loop. Now, a way to talk about the loop is what's called two-sided SLE. An SLE path, you think of it as going up. If you go up a certain amount, you can map it down. But if I want to go both positive and negative directions, I have to have a way to go backwards. And basically, that's not hard to do. Sort of, way to think about this, we take one function, maybe I'll call this f naught. And it depends on the particular point that I started with. But if I chose a different point, I could take f naught, then do something on this side, and then come back. And it's things on this side, I'm actually going to call the loops. So for SLE, we have forward Loewner chain and reverse Loewner chain. And in fact, for the purposes of this, we'll consider the CT as the SLE loop. And this is a perfectly well-defined probabilistic object. It's basically the same thing, except you go both forward and backwards directions. So now I want to talk about something which at least I found confusing in some of the notes I read, called the free boundary or Neumann GFF in H. So basically, here's the picture. We have this thing. Now let's choose a point. Over here, Z. And we're going to look at the field at this point. The field at this point has two parts. What's given by this loop so far, plus an additional GFF. If I map it over here, so there's maybe F naught and Z. I may put it on the wrong side, but that's okay. If I put it there, I can talk about the same thing, the field here. The field here, actually let me call this point C over here anyway. I'll call it C. I could talk about the field Z here, and I'll write the field Z here as two pieces. Where phi of Z is everything it felt from here, and then h of z is an independent field in the upper half plane. And we understand more or less what this is. That's a Dirichlet. Trying to understand this is a bit tricky because when I map from here to here, I now have a boundary condition, but there are two pieces of randomness in here. There's the randomness from the curve, so I no longer see the curve, and there's also the randomness in the field that was put on the curve. So somehow this boundary condition includes both of them. So in order to understand this, a lot of what I'm going to talk about is going to be just to understand this. It's understanding the reverse Loewner flow. So what am I going to do? Well, I'm at this point. I'm going to try to feel the field here, and I will do it by exploration, but I'll do it what I might call reverse exploration. I'll look at the part that's been created most recently first. So maybe I will look at here. Now that corresponds to something like that over there. And so it's going to be mapped up. From here to here is the reverse Loewner flow. It's driven by a Brownian motion. And it's only telling me the curve. And this is sort of well understood. So in this flow, if I start in the upper half plane, I always go up. The measuring part always goes up. If I start on the real line, I mess around on the real line until I hit the origin, and then I go up. So the z is the axis of positive stays on the real line until a certain time when it starts going up. But along with it, it creates a pairing of these points here given by the curve. Now here I've only used the randomness in constructing the curve. I haven't looked at the field yet, field on the curve. So again, I'm going to write, if I take a point zt of z, so this is zt of z, where I've always normalized this to be 0. I'm just going to write it as r of z plus ihz. Then I can write this field phi formally as the real part of the integral from 0, well, as phi infinity, where phi t of z is the real part of integral 0 to t, 1 over zs of z dws. Now, I write it like this because I like writing complex fields, even if but I really, you just think of this as ut of z plus I dt of z, where, and I think there should be no I there, just should be ut of z plus bt. There's no I, that's a misprint. Ut of z is equal to this, and bt is this. So what I've done is I've taken a complex Brownian motion, and I've let bt be the randomness of the curve, and bt star the randomness producing the field. And we separated them, and then bt is given by this. If you start in the upper half plane, they're not independent, because even though the Brownian motions are independent, the integrands are not. But in the limit, but you can take the limit as t goes to infinity, not for z, but you can take the difference. And this is because eventually I'm going to see the entire field, and I have that singularity at time minus infinity, and I still have that. And here's the key idea in the picture. At time t, ut of z is determined by the path of the curve. This is just has to do with the SLE path, the SLE curve being mapped. Vt of z is the expected value of the Dirichlet field on h at times, well, let's put it out here. If we think of the original segment, at time t over here, at time t, we get to see the residual field here. In other words, I've created a field here, and when I did this part, I only had a residual field. And what I'm seeing is the residual field there. Okay, let's see. It's decided to be slow again. Let's see whether it's moved over here. Okay, I have to go back a bit. Okay. If x is an r, then that's actually the same expression as I had before. Now I've just changed it to x's because and this is it's equal to this in this case, and that's until I reach the origin. Once I reach the origin, I move up. If I look at the point here, there is no ht. Ht is equal to 0. So until I reach here, this guy reaches here, I'm not seeing any of the field because the field here is only generated by what's over here. So you have to get to there before I get there. Okay. Okay, I do want to talk about random conformal maps, exponential to field. Okay. There's a lot of talk about the Gaussian field, but in the real life, the Gaussian field isn't what's interested. Most interesting are random metrics. And just a way to think about this, we're actually you can think of a random conformal map, I put that in quotes, which generate f prime. So a Gaussian field can be thought of as a random harmonic function in quotes. A random conformal map would be this, and we write log f prime as log absolute f prime plus I arg f prime. Again, just waving our hands. So the Gaussian field is a random harmonic function and corresponds to the log f prime, log absolute f prime. If we want f prime, what we need to do is exponentiate the Gaussian free field. So how do we do this from our perspective? The Gaussian free field comes from stochastic integrals like this. If I want to exponentiate stochastic integral, the simplest thing to do is you just take what's called the exponential martingale. You basically just take the exponential of it, but that's not a martingale. You have to compensate it to make it a martingale. And here, I haven't taken any expectations. I've made this so its expectation stays constant. So if I just took x for the fact, the expectations would not stay constant. So that's the normalizing term, if you wish, just on improbability. And the only difference between here, this is just factor 1, factor 2. This is if we're doing length. This is a factor for doing area. Oh, exponential. That's.
The normal order usually involves subtracting the expectation of this normal order. So I thought you want the expectations in the second term.
This is the running expectation of this. Yeah, it's just probability language for saying that. Yeah, so it's effectively it's just, yeah. And I'll just say there's two natural normalizations, either normalizing one, which I'm going to be doing, or sometimes you normalize, that's conformal radius. And I'll just say quantum length and quantum areas are obtained as basically limits of this over various measures. Limits as you let t go to infinity. The one I won't discuss, Liouville quantum gravity, at least in the sort of probability rigorous way, is just often is used to describe this limiting measure for areas when you integrate the integral of the field d area. It's a limit, but this gives a well-defined fractal measure, random fractal measure. At least if kappa is less than 4. For the rest of the, I'm going to assume kappa less than 4. Okay. But this is not what I'm going to do. I'm going to consider length measures instead. I want to do length measures. Okay. So there is ut of c. So it's just a function of the curve, and it can be written like that. If I take the exponential martingale of this is just an exercise in Ito's formula. You actually get z, absolute z prime to the d. And y, and this is just imaginary part of z, to the minus kappa over 8. And d here is actually the fractal dimension of the path. That's for z in the upper half plane. It's a little bit different if you're only in x where you don't have a y direction. You get this. Now, when I was reading material, this where it struck me where I learned all the stuff about the Gaussian field, and then I learned all about exponentiating the Gaussian field, and then I got these martingales, and for me, these were extremely well-known martingales. For those of us who work in SLE, these are exactly the kinds of martingales you do when you discuss things like the multifractal spectrum of the curve. Here, I have power 1 here, but you can also have other powers here. I should say something. I'm taking the exponential without a constant there, but that's because I've already put the constant into the field. So for kappa, I've done kappa with a certain covariance function. I don't want to worry about that so much. I do not need to do that. So these are well-known martingales, and they relate to what's sometimes called the natural parameterization of the Minkowski content of the SLE kappa curve. So I'm going to take a diversion here to talk about that, digression. Oops. Go back. Let's see, have we gone back yet? No, it's on the right. Oh, there it is. Okay. So now this is just about a path, about a random fractal path. So the SLE path has this particular dimension. Now, the d-dimensional Minkowski content is gotten by fattening up this curve a little bit. Fatten up the curve, take the area, take the limit of this as epsilon goes to 0 by the right scaling factor. And if this limit exists, you get the d-dimensional Minkowski content. For most deterministic sets in the world that aren't really extremely nice, this doesn't exist as written. And that's why d-dimensional Minkowski content is perhaps not so used in the deterministic world. But for random sets, we're finding that this is actually the very good way of measuring something. Hausdorff d-dimensional measure does not work because it gives 0, like I explained later afterwards. So this is becoming, and so in the case of the SLE curve, I did work with a grad student, Mohamed Rezai. We showed this exists and gives a non-trivial random measure, well, non-trivial measure on the curve. The curve's random, so it's a random measure. And that's called the natural parameterization. It's singular with respect to this capacity parameterization that was nice for giving the Gaussian field. And an important fact about this is that this parameterization scales like a d-dimensional thing. So if I had length, you would have the derivative of the 1 power. If I had, oh, that should be f prime of gamma of t, not f prime of t, f prime of gamma of t. But that's just the right scaling. Now let me talk about the exponential of GFF kappa restricted to a curve. So this is one thought I'll talk about how exponentials are done. So suppose I want to know what the exponential of an SLE path is on a curve. Well, here the curve is coming with parameterization. So there is a parameterization. But if I want to look at the exponential of the field on the curve, I only need to know the field on the curve. So I might as well construct the field only on the curve. So I will use my way of constructing it like this, although I have to reparameterize the H capacity in order to make sense. I can take this curve, I could reparameterize it. This gives me the field. But this blows up at C as I hit it. So we have to take some sort of limit. In this case, it's actually relatively simple. So here's the exponential martingale. Maybe you'll be happier the way I wrote it this way with the angle brackets. This is the same thing I wrote before, but that's the expectation value, if you wish. Quadratic variation in probability. Same thing I wrote. It's the expectation of HT of Z minus that. And what I do is I stop this before I actually get to Z. So let's sigma n of t be the time s, so that, think of this as being the distance is about e to the minus n. Then I can integrate that. Now here I'm integrating with respect to the original parameterization, this quantity, and we take the limit. And under some relatively mild conditions that hold in the case of an SLE path, this limit actually exists and gives you. So here what I've done is, just to be clear, I've taken an SLE path and I've done an independent field. So this isn't, I have a random curve and I've taken the exponential of an independent field on it. So I want to discuss something called quantum boundary length for the Neumann field, which is basically trying to take, say, if I take a thing 0y, I want to find 0y. I want to take the exponential, e to the phi x. I have x dx, and x has appeared. I'm just going to say this. The upper half plane is not the most natural thing to map to. It's the easiest, but a natural thing is actually the slit half plane rather than the upper half plane. And that x dx comes from taking the slit half plane and moving it to the upper half plane. That's it. We want to take the limit of this. And this limit, we take a limit, well, this limit, LT of y, if I put in phi t of y, will be defined point-wise, but the limit is not, but I'll be able to take the ratio of two things. I'm going to go quickly on this. I just want to sort of look at this. So here's my field. My field is something having to do with the curve and something having to do with putting a random field on the curve. When I exponentiate this, I get e to that times e to this. There's also, okay, there's also the compensator term that I'm just not putting here for the time being. Again, these are not independent, but these integrals have covariance 0 because bs and bs star are independent Brownian motions. I kind of want to see what's happening with this. So the effect of the first exponential martingale is to change the parameterization of the curve. So we have this curve. We think we're starting the curve. The curve is just a straight line, 0 to y. And its parameterization is x dx. As I move along, I first see what happens. Oops, didn't mean to do that. I first see what happens up to the time I reach there. And what happens here is this converts the length parameterization, the x dx, into capacity parameterization. But then this next part, then when the curve moves up, it converts from capacity parameterization to Minkowski content to the d-dimensional measure. Let me sort of like this. For the more problem, I think of this as a parameterization martingale for the reverse Liouville flow. So we take the image of 0y, and the image of 0y at a particular time might have two parts to it. There might be part of it that hasn't zipped up yet, and part of it that's zipped up. Eventually, it'll all be in the upper half plane. And that's the part that's still in the upper half plane. And this x is the same as c. Sorry, somebody's right. X is one real. That's x dx. And this is, well, something absolutely continued with respect to Minkowski content. And so for t large, this term becomes irrelevant. And then it's the second exponential martingale that exponentiates the GFF on gamma, this parameterization. So what I've done is I've taken, in the second half of the talk, the Neumann field, exponentiated it, and see how what it gives is a SLE path parameterized by the d-dimensional parameterization, and then looks at the integral of the independent field with respect to this. And all of this is not surprising given our initial view. Our initial view was we were creating a loop, and then we were doing that. Okay. I do have an open question. I wrote the free boundary field informally in this way. Therefore, there's also an imaginary part of this. So in this case, the real part of W comes from the curve, the imaginary part by the independent field. Is there an interpretation of the imaginary part of this field? More generally, are there other complex fields that should be considered? That's just a question. And let me just end just to tell people, I've really just touched one piece of a very big subject. And I just want to, in one slide, tell you about some of the other constructions. There's discrete loop measure or Brownian loop measure, which is a measure on loops. I'll just say the total mass of this is related to the logarithm of the determinant of the Laplacian. It can represent the square of the Gaussian field by the local time of the loop soup. There's an intensity involved, and that's related to central charge. And I will say this doesn't always require positive weights. That's one object. There's another object, I'll just say conformal loop ensembles are like SLE loops, but where there are a lot of them running around that don't intersect with each other. So it's an ensemble of loops. This does not at all discuss the limits of random maps, discrete models of random geometry, whose limits get to these, say, Liouville Quantum Gravity and things like that. And also, one of the hottest areas right now has to do with Liouville Quantum Metric. So if I have a metric, I can talk about the distance between 2 points, as basically the infimum of the distance over any curve getting them. And that gives an extremely interesting object that my colleague at Chicago, Ewan Gwynn, is doing a lot on, but I'm not, so I will not discuss that. So I think I will end there.
Questions? Maybe I'll start with one. So in the beginning, right in the beginning of the talk, you had an ordering of points for the random walk, and that ordering seemed to be arbitrary.
Yes.
While when you went to the Brownian analog, the ordering was very specific. You were along the curve, and you should have a specific distribution. So can you explain more about this?
But the choice of curve was arbitrary.
Um,
And the fact that I did a longer curve is just convenience. I could have done a little bit here, a little bit here, a little bit here.
So the connectivity was not essential?
Connectivity was not, I mean, connectivity was essential for that particular expression I wrote. But it's not necessary. I mean, and in fact, it's very natural thing to do with, well, one simple generalization of this is, okay, let's explore with a curve. We haven't done everything yet. Let's do another curve. Let's do another curve. And that's all perfectly okay. They don't have to be curves, but if they're not curves, it's harder to talk about the Poisson curve. You start getting into non-simply connected domains. You start getting, so at the high level, it doesn't make any difference whatsoever. At the computational level, maybe it does.
It's like this question, what's the difference between theory and practice? In theory, there's no difference, but in practice, there is.
Yes.
Please, any other questions?
I wonder whether it makes sense to consider these curves on Riemann surfaces, for example.
Absolutely, yes. And a lot of these things can be done on Riemann surfaces. That's not really my expertise, but a lot of it is, a lot of it builds just basically on the Laplacian, on the Brownian motion.
What are the added difficulties of this?
As far as I can tell, and I'm not the expert on this, there's not much more difficulty, except whatever difficulty of dealing with Riemann surfaces to begin with. However, there are interesting extra structures that occur when you start getting non-trivial genus. Or even in the plane, when you get to non-simply connected domains, again, the definition is doable, but what you're actually getting can become very interesting.
One thing which was very much emphasized by Sheffield and Schramm, and he was, is inside your construction, maybe you can explain more, is the fact that the Gaussian Free Field has a jump between the two sides of the level curve. And
right, that was the picture I was trying to draw there, where it was pi on one side and 0 on the other. So the rigorous statement of this, and I can't really make it any better than what they did, is that if I have the Gaussian field, there is a SLE that you can find going through that field. And then for that particular realization, you could write, given that curve, the rest of it looks like independent fields on both sides, but with in this case, pi added on one side. So, yeah, I mean, when you talk about boundary values of Gaussian fields are really just harmonic functions. So boundary value, think of a boundary value as being a harmonic function, and you're adding a harmonic function to the field. And on one side you add pi, and the other side you add 0.
So I always felt there is some Heisenberg quality to this, is that the mere fact of looking at the level, that specific level curve somehow creates this jump that maybe wasn't there before you looked.
That's too deep for me. So in fact, if anything, I'm trying to simplify, and I'm just trying to say sort of this construction of building the field with the curve. And by the way, what I said there is at least implicit, if not explicit, in the proofs of Schramm and Sheffield. It's not like this is new. This is
Okay, more, any other comments or questions?
Thank you for your talk. Since the Poincare upper plane is the limit of the compact hyperbolic surface, and I want to know that can we use the discrete Gaussian free field on the compact hyperbolic surface to study the GFF on the hyperbolic plane?
I'm going to cop out of this. I'm probably not the right person to answer that question. So I'd have to understand a little bit better what you're, for myself. And maybe you might be able to talk afterwards, but maybe not. I'm not going to venture an answer in public.
Okay. No other questions? Let's thank